right, welcome back. It's been a little while since you've seen my great face on video. Today I'm going to talk to you about light and pigments, and I'll go over the lab with you a little bit and give you some new material. So should be good stuff. Here we got light, here we got the colors of the visible light spectrum, good stuff. All right, let's have some fun. Okay, so in lab, we did a lab about thin layer chromatography. We called it TLC. And in that lab, we basically took markers and we ran them on this filter paper like this. So we made a mark across this filter paper. And what we were showing was that we know that markers are made of different dyes, different colors, or pigments, if you will. And we wanted to find out, what kind of markers were in them. Okay, so we took a blue marker, a green marker, etc., and we ran them on this filter paper in some water, and we found that as the water diffused up the paper, it carried the pigments with it, and the molecules traveled up that paper based on their size and their density. And so what we found was with the different markers that we tested, we found that most of them were not a pure primary color. The only one I think that we saw that was yellow. The rest of them we saw were actually mixtures of colors. And so what I was trying to show you was that thin layer chromatography is a way of separating out molecules based on their size and density. So why we did that was I wanted to make a parallel between those markers and plants. So plants are similar to markers in that they contain colors. Okay, they contain colors. And what we saw was that in the markers, most of them did not contain just one color. And in leaves, too, we can see that most leaves do not contain one color. Here's a green leaf, and in that green leaf, you can see some yellow, and you can see some green, and if you do it right, you can even see some blue in there. Here's a yellow leaf, and in that yellow leaf, you can see that there's some yellow and maybe some orange in there. Here's a nasty orange, red, green leaf, and you can see all those colors reflected appropriately there. Here's a red leaf, and here you can see some yellow and some orange and some purples and some pinks. And here's a kind of a purple leaf, and here you can see those different colors. So we're seeing that even in plants, that plants are not just one color, that they have many colors. Oh, sorry about that. I had a new marker. And so we're seeing many colors, not just one, in leaves. First stage of photosynthesis, which is about the absorption of light energy. So while doing this, we kind of had a brief conversation about light energy. And what we do know about light is that we know that light travels in waves. Okay, and so we know there's a couple things about waves that we can measure. We can measure wavelength, and wavelength is this right here. It's how long it goes from like crest to crest or peak to peak. And we can also measure frequency, and frequency is how often the waves appear in an area. Okay, so we look at like wavelength and frequency. We're going to just talk about wavelength. Okay, so wavelength is how long it is. So when we look at the visible light spectrum is the spectrum that you and I can see, people can see. We can't see UV light. That's sun, rays from the sun. We can't see infrared light. That's like heat light. Rattlesnakes can see that, but we cannot. We can see visible light, and we can see in a range basically right here from 400, so we can see from 400 to 700 nanometers. Okay, and that's the visible light spectrum, 400 to 700 nanometers. Okay, and that happens to be from violet to red. So I'm going to write VibGEOR here. Okay, and so when I write VibGEOR, that is going from a short wavelength to a long wavelength, 400 to 700. So most times when we talk about the visible light spectrum, we're going to say VibGEOR, okay? And we all learn Roy G. Biv almost improperly, okay? That would be only if we're talking about a long to a short wavelength and decreasing wavelength. Okay, so it's 400 to 700 nanometers, and I would just kind of guess that like every 50 is a color. I'm kind of overemphasizing, but it's a simple way of doing it. So 4, 455, 556, 657. It's kind of the easiest way to think about it. Okay, so VibGyor 400 to 700 is increasing wavelength. Okay, so what do we know about light and colors? Okay, and we're talking about absorption versus reflection. Okay, and so you've probably known this for a long time. Basically, you're either absorbing or reflecting. So, for example, I'll take this green shirt here. And so why is this green shirt green? Well, this green shirt is green because it is reflecting green. Now in this case, since it's a weird color of green, it's probably reflecting more than one color of green, if you will. But for simplicity's sake, it's reflecting green, and it is absorbing everything else. So it's absorbing Vib, not G, your. Okay, and so it appears to us because it's reflecting green. Now our eyes are backwards. Our eyes are absorbing the green and reflecting the other colors. Okay, so why is this basketball orange? Well, this basketball is orange because it is reflecting orange and it is absorbing Vib, G, Y, Okay, it's absorbing Vib, G, All right, and so it's absorbing those colors. It's reflecting orange. That's why it appears orange. So just remember that things are either absorbing or reflecting. Pigments are molecules that absorb light energy at very specific wavelengths. So we know about pigments. We have pigments in our skin. That's the reason that we tan. We go out in the sun and we have pigments in our skin. Melanin would be one of them, and you sit out in the sun long enough and it absorbs light energy and it changes color and you get a tan or you get burnt or whatever, or you get darker. Okay, so pigments are in people as well. In plants, there's a couple of pigments that almost every plant have. The main two are chlorophyll A and chlorophyll B. And as you can see, those are the green pigments. This is kind of like your blues and your greens. And this one's kind of your greens and your yellows. Okay, so they both provide a couple of different colors that they're absorbing. Okay, so chlorophyll A and chlorophyll B are in most plants. They're primary pigments. Okay, there's some other pigments. We call them accessory pigments, which just means that they are in less amounts, but they're basically in other plants. I should note that there's thousands of different pigments, but these just happen to be kind of like the main three that most plants have. Okay, they are carotenoids, which you can judge by the color, are your oranges. And there are anthocyanins, which this is actually an interesting group. It's kind of like your purples, your reds, and even some of your blues. So anthocyanins kind of a big group of pigments. And then lastly, your xanthophylls, which are your yellows. Okay, so these are molecules that absorb light energy at specific wavelengths. Okay, those are what pigments are. So what we do know is, going back to plants, we know that plants contain these pigments, and those are the actual colors that they are. Now, they don't have the color just to be green. That's just a bonus, if you will. So here's an example. Here's a graph of what the absorption spectrum of chlorophyll A is, and this just measures the percent of absorption. And so this is 100% absorption. So remember, it's either absorbing or reflecting. So if it's 100% absorbing, that means it's 0% reflecting. Likewise, if it's not absorbing here, that means it's really reflecting. So we got to keep that in mind. Okay, so this is chlorophyll A. So remember, chlorophyll A is your blues and your greens, right? So this is a blue-green plant. Usually they're green, okay? So look at what we see here, okay? At 400, this is going to be your violets. 450 is your indigos, your blues, your greens, your yellows, your oranges, and your reds. And again, I'm kind of oversimplifying, but it's easy if you do it every 50, okay? So look what's happening here, okay? It's really high in the absorption of your violets and your indigos. So since it's absorbing them, it's not reflecting them, okay? So you're not going to see this as a blue plant or a purple plant, okay? Here, it is definitely really low in here. All this right through here, right? And so what we can say for sure is that this plant is definitely reflecting blues, greens, and even your yellows and some oranges. Okay, so that's kind of why this is a green plant, because you get your blues and the greens, which are really dark, but you have your yellows and orange, which kind of mask that a little bit and make it a little lighter. Okay, so I can say pretty clearly that I think that this plant would be reflecting blues, greens, yellows, and oranges, and I would say that it's probably absorbing, based on this graph, this and this. So I would say it's absorbing your violet, your indigo, and your reds. Okay, so that's basically what you do with this absorption spectrum. You look at where it's absorbing, what it's reflecting. It's probably a green plant or a blue-green plant. Okay, so that's just an example of just chlorophyll A. Here's another example. This is chlorophyll A and B together, so you kind of look at it the same way, except now I've got 2 pigments instead of 1. So I know it's absorbing here and here. So even though this one is not absorbing here, this one is. Okay, and so I look at my reflection range is basically in here. Okay, and then my absorbing range is basically back in here. Okay, so what I can say from this plant, just looking at it, is I would say it's reflecting blue, green, and yellow. And then I would look back and go, okay, what's it absorbing? It's absorbing your 4 to 500 range, which is your violet and indigo, and your orange and your red here. Okay, so what's this mean? Means that since it has 2 pigments instead of 1, look what it changed. It means that it's actually absorbing more light than it did before. Before it wasn't absorbing any oranges. And so by adding this second pigment, not only do you overlap some of the other ones that you're absorbing, but you gain some light here in the orange range that you weren't before. So plants have multiple pigments so that they can maximize the sunlight that they get in a day, and they can absorb more light energy. Okay? So it turns out that plants have multiple pigments. They don't just have one. One plant, a green plant, doesn't just have chlorophyll A or chlorophyll B. It has dozens, hundreds maybe even, of different pigments. And so by doing that, you overlap all those pigments and you get all those different wavelengths of light that are being emitted throughout the day or the year or the week or whatever. And therefore, that plant is going to maximize that sunlight. It's going to be absorbing light all the time. And so look, if you look at this one dips here where it's reflecting, but all these others pick up the pace. And so when you look at this from 400 to 700, look, you can see basically every wavelength of light is covered because I've got 5 or 6 pigments in here that are taking care of that. So it's really important that plants have many, many pigments to maximize the amount of light that they can absorb. Okay? So just the last bit about this. This light absorption that we're talking about is crucial for plants. This is how they get their light energy to do photosynthesis. So this is really the first thing that happens. Keep in mind that the chloroplast is the organelle that photosynthesis happens in. Okay, and this is what it looks like. And remember that your chloroplasts are found in the palisade layer of the plant, leaf, so up in this upper half up here, right? Okay, and so what we have is we have light energy, which is hitting this plant. Okay, and it's coming down this way, and it's got to go in through the epidermis, into the palisade layer, into the chloroplast, and it's actually got to go through the chloroplast and get into these thylakoids. Okay, and so what's happening is the pigments that we are talking about are actually located in the thylakoid membranes. Okay, so pigments are found in thylakoid membrane. Okay, so stage 1, the light absorption, happens in the thylakoid membranes of the chloroplast, which is right here, these membranes all the way around the thylakoid. Okay, so that's where the pigments are located. They're little molecules that are stuck in there. So, have a great day. Love you, bye.